Good morning, everyone. We're going to continue and hopefully pretty quickly finish chapter 6 today and then get into some review problems. I posted some chapter 5 review content, and then there's a particular chapter 6 quiz we'll try to focus on here in class. What we're trying to do here is just finish electron configurations to try to see, in particular today, for some of the larger elements, how do we come up with their configurations. This periodic table here is somewhat useful, and we can reconstruct this pretty easily. If you notice that our S block over here just starts with 1s for hydrogen, then lithium 2s on downward. We have our first P block starting with 2. So the first time we have a P block is 2, because the first time you can have an L of 1 for P is when N is 2. And so 2P on downward. And the first time we can have a D is when N is equal to 3, because D is L2. So the first time we can have a D shell is the N equals 3. And then on downward for 4D, 5D, 6D. And then the first time we can have an F, which is of course L3, the first time we can have an L of 3 is when N is 4. And so our first F block is 4F, and then into the 5F. And we have 7 rows of the periodic table that have thus far been discovered. We mentioned that their physicists are pushing into the 8th row for some reason, but all the elements through the very last one have thus far been discovered. And so what we'd like to be able to do is just know what electron configuration we expect to find for these atoms. And we'll also see today that a few, actually several elements have different configurations than what we expect. But what we expect you to know is how to come up with what configuration you would think an element should have. Like for example, for chromium, it's just kind of spotting the nearest noble gas preceding chromium. You would look here, that would be argon. And I'll also show you on the next slide, I pulled out the periodic table you guys get with your exam. So of course your periodic table would have the element symbols on there. But you can give the configuration with respect to the nearest preceding noble gas, and then just kind of continue the configuration on. So that would be 4s2. And then chromium's 1, 2, 3, 4 across into that 3D. So we'd have a 3D4. Now, we'll see on the next slide that it turns out chromium has what we call an anomaly, and it has an anomalous configuration. It has a slightly different configuration than the one we expect. The actual configuration we'll see for chromium turns out that it's actually a configuration of argon 4s1 3d5. Now, I'm not going to expect that you memorize that, and there's going to be some basic ideas on why this might happen. The idea turns out that some configurations are more stable than other configurations. Sometimes a half-filled configuration is better than a nearly half-full configuration. But you'll see when I show you a slide that kind of shows us all the configurations that some of the anomalies aren't entirely predictive. Sometimes there's a group trend, sometimes there's not a group trend. So we're not going to expect that you memorize that chromium does this. But what you can imagine is that there's going to be a few configurations that turn out to be lower in energy than the one we might expect. I expect that you would predict this. So anytime we ask you for a configuration, we're always going to ask you for the expected or the predicted configuration. We generally try to not ask configurations that are anomalous. So like when we write a test, if I'm going to ask you for a configuration of chromium, I usually would try not to ask chromium since it has the anomaly, because I wouldn't expect you to memorize it. And then if you happen to remember it, I wouldn't want you to be wrong if you guessed it, if you know what I mean. So we usually try to give you elements on the test that don't have these anomalies so that you can just simply follow the rules for coming up with the electron configurations. So if we push into elements beyond the 3D shell, we're just filling into the 4P. So we're going 4P1, let me go laser pointer, 4P1, 4P2, 4P3, 4, 5, 6, etc. through krypton. And then we're restarting the next row of the periodic table. And so the next element I wanted to look at was technetium, TC, that's element number 43. And so for element number 43, our nearest preceding noble gas is now krypton. And then we're into the 5s. So we get 2 electrons into the 5s. And then we're 1, 2, 3, 4, 5 into the 4D. So some of the things that are, the things that we usually would test is, do you get the right preceding noble gas? Do you get the proper number for that S shell? Do you then get the proper number for the D? Do you get the proper counts going into those subshells? And then this particular subshell is half filled. So this is a particularly, I guess, stable configuration with that half filled D subshell. And so that's our configuration for technetium. Now, TC is an interesting element. It actually rarely occurs on Earth. For an element so small, it's one of the few elements that actually doesn't have a stable isotope that naturally exists. But it actually doesn't mean that technetium is not a useful element. We can synthesize different radioisotopes of technetium, and then it's often used in treatment of cancer. So a lot of radiation therapy involves this particular element, even though we have to generally synthesize that particular element. I believe in the Earth in total, there's less than a gram. If you could accumulate all the technetium that naturally occurs, it's like less than a gram on Earth. So kind of interesting for such a small element to have such a low abundance on Earth. Most of the other elements near it on the periodic table, not until you get above uranium, do you have elements that just don't exist. So it's not until element number 92 that we have just those elements have decayed into smaller elements already and no longer exist naturally. Okay, so let's look at one in the F block. So let's get to terbium, that's TB, element number 65. So for element number 65, we can picture it here too, it's down below. So element 65. Now, one thing that we could always double check is if you know the atomic number, that's how many electrons should be assigned. Let's actually do a double check on technetium real quick. We should have technetium as element number 43. So I should have 43 electrons assigned in my configuration. Krypton is element number 36. So krypton would have 36 electrons. And then plus 2, plus 5. So 7 added on to 36 is 43. So I do have 43 electrons distributed. So you can double check a configuration, making sure all the electrons have been assigned into the configuration. And so for terbium, should have 65 electrons. Now our nearest preceding noble gas will be the next one down, which is xenon. So xenon would be our preceding noble gas. Xenon is element number 54. So that has 54 of the electrons within its configuration. So xenon would be all the way through 5s2, 4d10, 5p6, and then continuing into the next row would be the 6s for 2, and then we're into the F block. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and I wrote the wrong thing. This isn't the F, it's not a 5D, it's the 4F I'm filling into. So it should be a 4F, so I'm filling into the 4F. So that's another thing we would test. You put these into the D next, or you put them into the F next. Well, we're filling into the F block next. And the way you can see this on this periodic table is that you're filling into the block of 14 before you get back to the block of 10. So we're gonna get across 14 elements, and then we're gonna fill into the next D shell. So it's not gonna be until we get past the end of the F block, YB, that's ytterbium, or ytterbium. As soon as you get past that element, then we're filling into the 5D subshell and continuing along. To double check the electron count, 54 plus 11 would be 65. So I've assigned all 65 electrons. So again, you can double check the 2 plus 9 plus 54. Does that equal 65? And it does. So you can count up your electrons that have thus far been distributed. And let's look at one more, at least on this slide, for uranium, element number 92. We said this is the largest natural occurring element on Earth. And so element 92, it's here on the periodic table. We're then getting past radon, which is element number 86. So element number 86, that nearest preceding noble gas. Then we're filling into the 7s, 2, and then 4 across the F. And not the 4F, but now the 5F. So 7s2, 5f4. And then radon with 86 of the electrons plus 6 equals 92 electrons. Now, I think uranium is slightly different. Let's take a look at, let's take a look at the periodic table you get with exams to make sure you see how to take in information on the periodic table that you get along with your exams. Notice that this periodic table has a better construction than the one on the wall here. I mentioned before that I don't like this periodic table for like 2 reasons. One, lanthanum and actinum are shown up in the D block when they really should be down with the F block. And then if anything, LU and LR should be in the periodic table. But what periodic tables usually do is they leave a gap here so you can picture these 2 elements here are filling into then here. So that these are then filling into the 5D and then the 6D. And then continuing across the 5D, then across into the 6D. Okay, and so, and then again, to point out that the F block is shown down here, so you can still find your elements like terbium and uranium from the previous example. So that's how we put together bigger configurations. Yeah, so then let's take a look at which configurations are actually not the ones we expect. So the next slide from the notes then looks at, let's take a look, or I just pulled this out from the supplemental info for the exam too, just to show you this is the info you get with the midterm. If you haven't seen this yet, a bunch of constants, including things like the Rydberg constant, speed of light, Planck's constant, etc. A bunch of equations that you get that relate to chapters 5 and 6. So refer to this as you're working on practice exams. If you're working on practice quizzes, you might just have this open so that you can use the same sample info you get with the real exam. Okay, so with that, let's take a look at which configurations are different than the ones we expect. And let's begin with the configurations that are exactly as we expect. So like our S block is exactly S1, S2 for the alkali, all ending in S1s. Alkalins, all S2, exactly as we expect. The P block elements are all exactly as we expect too. P1, P2, P3, P4, et cetera, across. And then that trend is the same if you look the whole way across. So there's no anomalies within often what we call the main group. The main group elements are the S block and the P block. So no anomalies there whatsoever. Nothing going on. Where we see anomalies are with elements like we mentioned chromium. So notice chromium's not a 4s2 3d5 or 4s2 3d4, it's really a 4s1 3d5. It still has the same count of electrons. It's not that we changed the total electron count, we just moved 1 electron from what should have been in an S block into the D block. So the electron counts are still exactly as you expect. Copper does this too. So copper has a 4s1 3d9. We would have expected it to be a 4s2 3d9. So you see just one of the S block electrons was promoted into the D block in its most stable configuration. And again, I don't expect that you memorize that, but it just turns out that that's the case for copper. Now, interestingly, some elements do this the whole way down, like silver does the same trend, and then gold does that same trend as copper. And so we see like an interesting group trend where all of these elements here do the same basic trend. Now, when you get into some of the larger elements, Röntgenium, you may look and say, well, it doesn't follow the trend. Well, it's such a large element. I don't think anybody's really truly studied the configurations of some of these elements that exist for such a small period of time. And generally only a small collection of those nuclei have ever even been synthesized. Just enough of the atoms. I think it takes 3 or 4 nuclei in total to be synthesized in order for physicists to declare that they've synthesized that new element. So there's not a whole lot that's known about some of these really large elements. But then if you look at something like nickel is just the ordinary configuration as you expect. So nickel's the normal configuration. Notice palladium actually moved 2 electrons from what should have been in the 5s2 into the 4d. And then notice platinum, for some reason, moved just 1 electron into the 5d. So it's not even periodic. The trends make really, in some ways, no sense here. So I don't expect that you memorize that nickel's normal, but then palladium and platinum have an anomaly. Ruthenium and rhodium do something really odd in that they are forming configurations with an S1 and D7 and D8 configuration for no apparent reason that I can make sense of. So we see some peculiar ruthenium and rhodium configurations. And then molybdenum has that same configuration like chromium does, but then tungsten has the ordinary expected configuration. So it's kind of a free-for-all. So I just wanted you to see that some of these configurations are a little bit different than what we expected, but I don't expect that you memorize those anomalies, but we call those anomalous or just the word anomaly. So they just appear to be cases of configurations that go against our rules. And then we also see a bunch in the F block. So if you notice, some are Ds and some are Fs and some are combinations. Like generally we're filling into the F block, but sometimes electrons can be promoted into the D block. So you can see gadolinium does this. Terbium's exactly as you expect. Most of these as we continue as we expect. Holmium, element 6,7 is exactly as we expect. And then getting across into the next F block, we see kind of the same basic idea that there's some movement of electrons between the D and the F, especially for the first half of the subshell. And then as you start getting across into these larger elements, then they're more or less the configuration you would have expected. So a little bit of a deviation in the F block, a little bit of deviation in the D block. There's some rhyme and reason. Maybe there's some configurations that are more stable. That would have to be the explanation, but why those configurations are more stable is hard to understand and hard to interpret. Okay, so we see some anomalies. A question you might expect is if you know or are told a configuration, well, you should still be able to figure out what the element is. So we expect that if we give you a configuration, whether it's the expected or the anomalous, just count the electrons up, see how many electrons there are. That will tell you the atomic number because these are all neutral atoms. So if we give you a configuration and say, what's the element, just count the electrons up and then look for the atomic number associated with that electron count. And then you could also answer questions like how many unpaired electrons are there. So let's say we tell you chromium has this anomalous configuration of the 4s1 3d5. How many total unpaired electrons? Well, we're just picturing there's one 4s with one electron because we have one 4s, and then there's 5 3d orbitals, which we spin pair the electrons into each of the orbitals to make the best use of space. So we end up with our 3d5 and the 4s each having unpaired electrons. We have 6 total unpaired electrons. And there's experiments that track how many unpaired electrons an atom has. That's how we learn these details in the first place. So the way we end up learning about configurations and supporting and understanding why the configurations are as we expect and the ones that we write are from being able to do experiments that determine how many unpaired electrons a given atom has. And so chromium and this is interesting too to point out that we're talking about like a gaseous atom of chromium. Like an isolated single atom of chromium, we would expect to have 6 unpaired electrons. Okay, so that kind of wraps up the notes for chapter 6. We're going to circle back to chapter 5 with some review first. I probably won't get to too much of the chapter 6 review today. There's a bunch of practice quizzes. I'll probably make a video if I can today, if I have time, of the chapter 6 problems I want to do next week, because I might have to go pretty quick and maybe only do some of the problems from that chapter 6 part 2 chapter review from the daily quizzes. But I'll put a video key for that up so that you can check against the key if I don't do every single problem before class next Monday. And I'll get the class early next Monday like I do for midterm weeks. So we'll start class Monday 7:40 with some review. Unfortunately, we have to spend some time on Monday moving into the next chapter. Okay. So let's take a look back at like the early part of chapter 5 and getting into the discussion of what we hope you can address questions with regard to like work and heat exchange. So here we have a balloon filled with room temperature air. If you're looking for these problems, they're in the chapter 5 review packet in lecture slides. So there's a separate packet that has this page, and then the remaining problems are daily quiz problems, but they're also in a packet I put together on Carmen, so you can easily see the questions we'll look at today. But a balloon filled with air at room temperature is immersed in liquid nitrogen. Now, liquid nitrogen has a temperature of 77 Kelvin, and so the balloon shrivels up, it contracts, and so then for the air inside the balloon, what would we make of the sign of Q for the air and work for the air? Did the air in the balloon absorb heat? I don't think it absorbed heat because it cooled down, so it gave heat off. It lost heat. So, and then losing heat would be exothermic. Now, sometimes this gets a little confusing because you may say, well, I thought exothermic reactions got hot. Well, this reaction here is the reaction to being placed into a cold environment where the air was warm, the air became colder, so the change of the heat of the air is that it had to lose heat in order to drop the temperature. So the temperature of the air simply went down, so therefore the heat of the air had to drop, and so therefore the air lost heat during the process. So we're looking at answers C and D as being the right answer, rolling out answers A and B. And then what about work? Did the air receive work or did it do work? It received work. It had work done on it. So expansion would be air doing the work. So if we had a balloon that was warmed up and then it expanded, then the expansion would be moving the surroundings. That would be the air doing work. That would be negative work. This is the balloon receiving work, which is positive. So the W would be greater than 0 for the air inside the balloon. It received the work that was being done by the surroundings. So work was done on the air by the surroundings. So work done by the surroundings is positive in terms of the system it's working on. And then the opposite would be if the system expands into the surroundings, then that would be the idea of negative work. That would be the system doing work on the surroundings. Okay. Let's take a look at a problem that gives us some numbers, and then the real question of this being the interpretation of the sign of the number. But what is the sign of Q and W? And then hopefully we can calculate delta E as well. But what are the signs of Q and W for a reaction or system? And system and reaction are kind of the same idea. So a system is just our thought of a reaction that releases 47 kilojoules of heat. And it probably should say of heat to be slightly more clear. So it releases 47 kilojoules of heat and then absorbs 21 kilojoules of work. And so if we release heat, that's negative, so that sign of Q would be less than 0. So that should be negative 47. And if we absorb work, I guess it's the same example above, but that would be positive. So the work, absorbing work from the surroundings, this would be 21 kJs. So absorbing work means that the surroundings does work on the system, is what that means. If we release work, then we're working on the surroundings. That would be negative. So the work should have a positive sign. The delta E is equal to Q plus W. Now this is like the classic equation. This equation probably in that form, I'm assuming, and I'm almost certain it's on that equation sheet that I showed earlier that you get with the test. But this would either be delta E system is the Q system plus the W the system, or the delta E reaction is the Q reaction, W reaction. It could be the delta E surroundings is the Q surroundings plus the W surroundings too, but we usually don't flip it that way. But you theoretically could flip all the signs and then calculate this for the energy change of the surroundings of the reaction. But this is just showing that the delta E, the system or the reaction, would just be the sum of the Q, which is minus 47 kJs, and then plus, and then the sign of work is plus 21 kJs. So just 47 negative plus 21, and that should be negative 26 kJs. So the delta E of that process is, the process loses energy. Now, is the process exothermic or endothermic? That's where you just look at the sign of Q. So the sign of Q is telling you exothermic or endothermic, so that would be an exothermic process. So for the question of exothermic, you just look at the sign here and say that would be exothermic for releasing heat. And then releasing, absorbing heat, of course, would be endothermic. The sign of delta E, we don't define those terms, but that's exoergic, endoergic are the terms that you use for the sign of delta E. So if you're thinking, well, what does the sign of delta E mean? We just would put a different word on it that we wouldn't expect that you know. For most of the problems we look at with reactions, once we get into like section 5.4, we're really getting into open system or chemical systems where work is small or negligible. And so that the heat change of the reaction is the delta H. And so we're primarily just focusing on delta H and Q for most of the chapter and don't come back a lot in our math problems to really looking too much at W. Let's look at a couple more interpreting signs of Q and W. So we have a combustion engine that's burning gas to accelerate a car. And so at the moment that the car is accelerating, can we calculate the sign of Q and W, but with respect to the chemical reaction taking place in the engine? So for that reaction in the engine, is it releasing heat, and is it releasing work, or is it absorbing? So the combustion reaction, of course, is taking place with a kaboom. It's taking place with a flame. So heat is certainly being released by the reaction. So the Q, by nature, for an exothermic reaction is exothermic. So that's just by nature. So the sign of Q and W for the combustion reaction, so the reaction releases heat, the engine's going to warm up. If you imagine we start the car, cold engine block, we're accelerating down the highway, the engine's going to become warmer as we go, and then the car is going to accelerate, which is it receiving work, so the car receives the work, so the reaction is doing work on the surroundings by moving the surroundings. And so we're releasing energy in terms of work by physically moving the car. The important word here is that the car is being accelerated because the work is a force applied times a distance, and a force is a mass times acceleration. So accelerating the car is applying a force to it to make it move. And so that's the releasing of energy to move the car. And so this is the classic example where Q and W have the same sign as each other, and they're both negative. And I think this makes a lot of sense in terms of thinking the combustion reaction definitely takes place with the flame, definitely releases heat, and then it's definitely moving the car. That's the whole purpose of it, is for it to do work on the surroundings. Now the surroundings receives the work. If you said, what's the W sign for the car? It would be positive because it received the work that was given to it by that chemical reaction. Let's do another problem of two gases in a container. Two gases are in an airtight container with a movable piston, which can expand if a gas is created, contract if a gas is consumed. It's just going against atmospheric pressure. So presumably the container is just maintaining a constant pressure. So if gas is made, it's going to expand. If it's consumed, gas, the container volume will drop. And so the system is also submerged in water, so that the heat from the system can go into the water bath. So we can look and see, does the water temperature change surrounding this container? So as the gas reacts, so the gases are reacting inside this container that has a movable piston that's surrounded by water. And so then the piston contracts, and then the temperature of the water in contact with the system increases. And so the temperature going up for the water, that's the surroundings. So the surroundings temperature goes up, and so the heat of the surroundings goes up, therefore. And so since we have the opposite relationship to the reaction, the heat of the reaction had to drop. So the reaction had to release heat that went into the wall of the container that then went into the water to increase the water's temperature. So the water is, of course, the surroundings of the reaction, and so that allows us to see that the heat of the reaction is actually dropping and the reaction is exothermic. And then the W, we're getting contraction of the container. We're consuming a gas by the process of this reaction. And so the consumption of gas leads to the contraction. That's the surroundings working on the reaction. And so that would be positive. We have contraction here. So expansion would be negative. So contraction is positive. So it should be Q negative, W positive. Now, what's the sign of delta E? So delta E would be the Q plus W, but do you see how we wouldn't know? Like, we'd have to know, well, how much heat was released versus how much work was done. So we actually don't know anything about the sign of delta E. You might think that just because the process took place, it should be negative, but that's not even true per se, because there's something called entropy. So the entropy is something we don't know about. We'll learn about that in chapter 20. Or I think 19 actually, but not chapter 19 in Chem 1220, you'll learn that there's a thermochemical property called entropy, and so it's the delta H and the delta S that combine into something called delta G that allows you to know if that sign's negative, then the reaction should take place, not necessarily delta E. So we actually cannot determine delta E without more information. The only way that you can know the sign of delta E is either by knowing the numbers that you can plug in, like the previous page, or by knowing that both that both Q and W are both negative or both positive. So if Q and W both have the same sign, then of course we know the sign of delta E will have to have the same sign. So we're just adding those together. So when we're adding together a heat with one sign plus a W with the opposite sign, we need to know the actual magnitudes to be able to calculate and determine delta E and its sign. So let's say you have a reaction taking place in a flask. I have no idea why my handwriting just randomly sometimes disappears. It'll be in the video later, and I should be able to get it to actually appear in the notes. Here, let me. Okay, so I can apparently get it to reappear, although. Okay, so here we go. So into the last question. So on this page. So when a reaction occurs in a flask, you notice the flask becomes colder. What's the sign of delta H? Now the sign of delta H is for the reaction. And that's like, when we say delta H, what's the sign of delta H for the chemical reaction occurring in the flask? The temperature of the flask is the surroundings. So the temperature of the surroundings is dropping. So the heat of the surroundings is dropping. So therefore, the heat of the reaction had to increase. The reaction absorbed the heat. The reaction took the heat from the surroundings. That's why they became cold. Now you may say, well, if it took the heat, why doesn't it feel warm? Well, the heat was used to change the bonding nature. Some chemical reaction took place. The heat was absorbed so it could rearrange the bonds, and that's where the heat went. It didn't go into temperature. It didn't go into making something warmer. It went into physically changing the nature, and it took that energy by the process of the reaction occurring so that the surroundings felt colder. And so this should be an endothermic process. Q is positive for the reaction. So therefore, delta H is positive. So delta H is just the heat change of the reaction occurring, especially in an open system, open container, open flask here, etc. Get into some more numerical questions. So the enthalpy of solution, we're told, for sodium hydroxide solid in water, what that means is it's the heat associated with that compound dissociating in water. We know from chapter 4 that when these two substances are added together, we should get the ionization of sodium plus and to the hydroxide ion. That we should form those two ions in solution. And so that's what's causing, that's the basic chemical reaction taking place, is just the dissolution of an ionic compound. And then there's a heat associated with that. The heat is negative, so the reaction releases heat into the water when that reaction takes place. And we're told it's minus 44.4 kJs per mole of sodium hydroxide. So if we take a sample of sodium hydroxide that's about 13.9 grams and put it into 250 grams of water, we do this in a coffee cup calorimeter. Now the only idea of a coffee cup calorimeter is just an insulated cup. It's just a cup that's insulated from the outside so that all the heat from the reaction that it gives off or any heat that it absorbs comes only from the solution, only from the cup, the inside part of the cup. And so it's just an insulated cup. It would be perfect to do it in like a Stanley or a nice kind of container like this that's relatively insulated from the outside so that all the heat change is just confined to the container. And so then the temperature changes initially from 23 degrees to what temperature? So we're trying to figure out what temperature the water changes to by the nature of this reaction taking place in it. Now, we did problem before, like when we did this problem in class, when we introduced coffee cup calorimetry, what we did was we gave you the delta T, and then from that information, we could calculate eventually the heat change in the calorimeter, and then from that, we were able to then go from the heat per amount of compound, what was the kJs per mole. So we kind of had that process before for this problem, but here we actually give you the enthalpy of solution. We give you that kJs per mole quantity, and then we ask for the delta T. So it's a very similar problem. We're just going to solve it first by thinking, well, what's the heat change that 13.9 kJs per grams of sodium hydroxide will undergo? So how much heat does that quantity of the 13.9 grams of sodium hydroxide have to change within the water when it's added to the water? So what I'm going to look at first is the 13.9 grams and this minus 44.4. And what I want to calculate is the Q of that reaction. So I want to calculate the heat of the reaction where I have 13.9 grams of sodium hydroxide. And the molar mass is, I think, 40.0, 22.99 sodium, call it 23.00 for sodium, plus 16.00 for oxygen, 1.008 for hydrogen. Yeah, so 40.01 grams per mole. If it wasn't obvious why I'm going grams to moles, I'm just going grams to moles because my kJs per mole is in kJs per mole. So I'm just looking ahead to that I want to use minus 44.4 kJs per mole here of sodium hydroxide. So I had to convert to moles to get this to cancel. And then let me do one thing here too. Let me go ahead and convert this to joules. And the reason why I'm going to do that is I'm just looking ahead to this unit here on a specific heat in joules per gram Kelvin. And so at some point I'm going to have to convert either that to kJs or the kJs here to joules. So let me just convert this to joules. So 1 kJ, of course, is 1,000 joules. And so then 13.9 divided by 40.01 times 44.4 negative times 1,000. So I get negative 15,425 joules. So I have about a third of a mole of sodium hydroxide, and I have about then, a third of that minus 44.4 kJs of heat to release into the water or absorb into the water. Is this going to release heat when it dissolves in water? Yeah, this is going to release that heat. So this is the amount of heat that's going to be released. The temperature of the water, which is the surroundings, of course, the temperature of the water should increase because we have that exothermic reaction taking place. We have the reaction's going to lose heat, and then the surroundings is going to gain the heat that's given off. So the reaction loses the heat that goes into the surroundings. So the temperature should go up. So I can actually rule out at least that the temperature is not going to drop for the water. So I can at least rule out one of the answers here. Okay, so then how do I then relate this to the specific heat of water, or the specific heat of the solution, really? So the solution is assumed to have the specific heat of that of water. So the heat change of the reaction is the negative the heat change of the surroundings. That's the main idea, is that whatever the heat change of the reaction undergoes, it's the opposite sign for the surroundings. And then the surroundings is the solution. So you can write the negative Q of the solution because the solution is the surroundings. It's what surrounds the chemical reaction. And then the solution can be described by that MCS delta T. And so the two important things here, I think, are seeing that the solution surrounds the reaction, and then that we get this minus sign. The minus sign is just simply following from the heat of the reaction is the opposite of the sign of the heat of the surroundings. So it's very fundamental in how we get that minus sign. And so I have minus 15,425 joules. If I'm paying attention to sig figs, it's 3 sig figs. Not a lot of sig figs on this test. But then negative sign from our equation, mass of the solution. So I have to put the mass of the entire solution. So that's going to be the 13.9 grams of sodium hydroxide plus the 250.0 grams of water. So that ends up being 263.9 grams because I want the solution mass. Then times the CS, the specific heat, 4.184 joules per gram Kelvin. And then let's just leave this as delta T and calculate the delta later. So let's just leave that as the temperature change and solve for delta T. You see how I'm going to take 15,425 and just divide by, so my joules are canceling and the grams are canceling. So I'm going to solve for my delta T just by taking 15,425 negative divide by negative 263.9 and divide by 4.184. Of course, dividing by the negative sign, that gives me a delta T of plus 13, call it 14.0 Kelvin or degree C. Now let's leave it Kelvin, just to make sure we drive home this message one more time, because that's the unit we get out here is just still in Kelvin. So the temperature goes up by 14 Kelvin. Now, if we want to like play the Kelvin game, then we would convert 23 to Kelvin. So 23 to Kelvin would be 23 plus 273.15. That temperature conversion equation is on the test. That's 296 Kelvin. Add 14 Kelvin to that. So our final temperature should be 310 Kelvin. Subtract 273.15, and I get 37 degrees C. Now, if you were like, wait, what? Like, it's not even that complicated, right? Because the delta T could also just be equal to 14.0 degrees C. Because the delta T going up by 1 Kelvin is going up by 1 degree C. So the temperature is just going up by 14 degrees C. So just the temperature units, as long as you're being thoughtful here, the 23 goes up by 14 degrees. That's the same as going up by 14 Kelvin. It's not saying 14 degrees Celsius as an absolute temperature is the same temperature as 14 Kelvin. It's saying that a 14.0 Kelvin increase in temperature is the same increase as a 14.0 degree increase in temperature. 1 degree Celsius change is the same as a 1 Kelvin change. For some reason, the degree C in Kelvin messes a lot of people up here. If you want another way to solve this problem to not run into that issue, that this is just equal to the same unit in joules per gram degree C. So just know in the delta T lingo, degree C and Kelvin are interchangeable. And the key, too, is that by the equations, our delta T goes up. TF's higher than TI, so the temperature goes up during the course of this exothermic reaction. Question 6, looks at a bunch of questions. You know what's funny? Like, I'm glad that we give our tests on Karman now, because we used to have a lot of questions on tests like this, and if you mess one little thing up, you get the whole question wrong. So at least now when we ask a question like this, we ask it like in 4 parts, and you can get each part right or wrong. But anyways, each question here, a reaction with a negative enthalpy change is exothermic. That's exactly the definition of exothermic, is it's a negative delta H for the reaction. A reaction occurring in a closed system, delta H and delta E must be equal to each other. That is like whether or not the system is open or closed, delta E and delta H are different from each other. Delta E is Q plus W, and then delta H is the heat change of the reaction if it were in an open system. Even in an open system, delta H and delta E aren't equal to each other. So in no system would delta H and delta E be exactly equal to each other. So that would be incorrect. Not true. An open system can exchange matter and energy with its surroundings. That's the definition of an open system. It's like an open container that can have heat exchange and energy exchange. A closed system can exchange heat but not matter. And then an isolated system can't exchange anything. Can't exchange heat or matter. That's correct. And then delta H and delta E are state functions. What's a state function? State function is a path-independent function. Delta E and delta H are path-independent. So this just means path-independent. And they both are path-independent. So that means it doesn't matter how you go from A to B to C to D. A to D still has the same delta H and delta E no matter what process you take. Now, the amount of heat or work you can have a reaction do depends on the type of reactions and the way you carry them out. So Q and W are not state functions. So they depend on how the processes are carried out. So imagine a combustion reaction occurring in a car. You can get all heat, you can get all work, or mostly all work, or some combination of the two. So it depends on how you're carrying the reaction out, on how much heat or work you're going to get out of those reactions. The sum of the two go to delta E, and then that's a path-independent function. But delta E, delta H, path-independent. That just means path-independent functions really means you can flip them, you flip the sign, you can double them, you double the magnitude. Q and W, it's like you need to know way more information to know how changing a process would change Q and W. Okay, so we have 1, 3, and 4. I didn't read it right. I read it as both delta H and delta E. It's saying neither are state functions. So reading comprehension fail for me, but I did at least it wasn't an option, so at least I could correct myself and see that, no, I read it wrong. So they are both state functions, so neither of them are state functions is an incorrect statement. Okay. So it should just be 1 and 3. That's why I hate those kinds of questions. So what's a formation reaction? So question 1, this is from practice quiz 26, is saying which of the following reactions represents the enthalpy of formation reaction of the compound ethane? So the enthalpy of the key word here is the enthalpy of formation. So an enthalpy of formation reaction forms the compound on the product side. So the compound has to be on the product side by itself with nothing else. So A would be wrong because of the presence of H2. So we have to form 1 mole specifically of that product as well. So we form 1 mole of the product on the product side, and then we have whatever the constituent elements are of the compound on the right side and their most stable form at room temperature. And so for carbon, I mentioned that technically it's carbon solid graphite, but usually we just say carbon solid to not litter up a page with extra information. But 2-carbon solid is exactly what we would expect you to note for the ground state of carbon, or the most stable form of carbon at room temperature. And then H2, hydrogen should be H2 gas. And then we balance out the proper number to give us the right numbers in the formula. We can leave fractions. If we have fractions, that's okay in this reaction because we always form 1 mole of the product. And so then C is of course wrong because that's not an elemental form of the elements. Same thing here as A, so that doesn't make any sense. And then this is wrong because H, gas, is not the most stable form of hydrogen. H exists as H2. Hydrogen's H2, oxygen's O2, nitrogen's N2, F2, Cl2 for fluorine and chlorine. Br2 and I2 are also diatomic molecules. Technically, bromine's a liquid, iodine's a solid. I don't know if we'd expect you to memorize that or know that, but everything else like H2, N2, O2, F2, Cl2, those are all gases. Now, how do we use delta HF values? Well, we can easily calculate a delta H of reaction by summing the delta HFs of the products minus the reactants. So we're just summing up the products delta HFs, taking note of the physical states to make sure. Sometimes we'll give you some extra molecules, so you have to carefully look for water liquid to make sure you have the water liquid one in the reaction, and you subtract the reactants, and then the element here we have to sometimes recognize as 0, that the delta HF of hydrogen isn't given here because we expect that you recognize that's an element in its most stable form. So that would just be 0. So we'd be doing 3 moles times the CH4. So I do 3 times negative 74.85. And we're summing up. So I go plus 1 mole times the CO2. CO2 is negative 393.51. And then again, plus, and then 2 times for water, it's negative 285.85. And then subtracting the reactant, sum of the products minus the reactant, so then I'm subtracting 4 times CO. And then I try to be very deliberate with the plus and the negative signs and putting them in. I try not to do the plus minus math in my head because I usually screw it up. But I get negative 747.6, this answer here. So again, sum the products, delta HFs, and then subtract the sum of the reactants. And so that's adding up the products, adding up the reactants, subtracting the difference between them. What amount of heat is released by this reaction here? It's minus 2601 kJs, but it's for 2 moles of this, 5 moles of that, 4 moles of this, forming 2 moles of that. So the moles are as indicated by the given balanced equation. And so when we have 3 grams of C2H2 combusting, the heat that's released, the heat of the reaction would be, we take the 3 grams of C2H2, we have to take its molar mass. That'll be about 26.0 grams per mole. But then the key is, and this is really the big key, for every 2 moles of C2H2 in that balanced reaction, the delta H was minus 2601 kJs. I have to inspect and get that 2 here. So the minus 26.01 is per however many moles of that substance there were in the balanced reaction. So I go 3 divided by 2601, or sorry, 3 divided by 26.0, and then times negative 2601. So the Q of the reaction is minus 300 kJs. The reaction loses 300, so the reaction is going to release that 300 kilojoules. Oh, I forgot to divide by the 2. I made such a big deal out of making sure to see the 2, and I forgot to hit the divide by 2 in my calculator. Again, I'm saved by the choices not having the wrong answer because I forgot to put that into the calculator. Hopefully I'm giving you a lot of good things not to do on the test. But it would be 150. 150 kilojoules is released by this reaction. Which substance is defined to have a delta HF of 0 for sodium? And sodium's a metal, it's solid, so it's a sodium solid. Not the AQ, not the gas, not the liquid. Those would all have an enthalpy associated with their formations. It's only the elemental form, the most stable form of sodium, the form that exists at room temperature. A quick Hess's law problem. Now, I don't have a whole lot of time left, but if I'm doing this on a test, I'm just like kind of noting I need 2 irons. So I need to double that first reaction. It's in the right order, it's in the right direction. The second reaction, I need to flip it, is all I need to do. I need this over here on the product side. So I just need to flip that reaction, and then everything else more or less cancels out. So if I could write these out, show the flipping, but all I really need to do is see I need this over here, 2 of them, and it's on the reactant side, so I flip the side here, and then I double the magnitude here. So it should be 2 times negative 341 minus 115. So I get 799 negative. Link, it's just in Carmen for the quiz for today. Now, bond enthalpies, the main thing I want to mention is the equation is on the equation sheet. If you go to the sheet you get with the test, but it's the reactants bond strengths minus the products. So it's the heat that we need to undergo to break the bonds in the reactants versus the heat that the product bonds form. So it's the sum of the reactants bond strengths and then so sum of the reactants bonds, and then we're subtracting the sum of the product of the bonds strengths. We have 2 choices. So it's the reactants minus products is what I'm just trying to quickly write. Now, the 2 approaches you have are to break all the bonds in the reactants and then form all the bonds in the products. There's nothing wrong with that. It might take you a little bit longer, but you really only need to break the net bonds that are broken. We're really just breaking the carbon-carbon double because I still keep all the CH bonds. So all these CH bonds, I have 5 here, and I still have 5 here, and I still have the carbon-carbon triple. So the only thing I'm making here are the 2 carbon-carbon singles. So I'm breaking the 614 kJs per mole for the 1 bond, and then I'm forming 2 times the carbon-carbon single bond of 348. So it should be 614 minus 2 times 348. And the key is seeing that those are the only net 2 bonds that are changing, and then it's also reactants minus products. So bond strengths, and it's also a prediction, not a direct calculation. So we're approximating bond strengths with this technique, not an actual accurate calculation, 100% accurate. So it's just a way to approximate bond strengths, but it's a way to see that exothermic reactions generally have stronger bonds in the products than in the reactants. Endothermic reactions usually have stronger bonds in the reactants than they do in the products. So it's just kind of seeing the nature of exothermic versus endothermic reactions comes down to relative differences in bond strength is the main idea here. All right, guys, we'll wrap up our Chapter 5 review. We'll look at some Chapter 6 content on Monday. Have a great weekend.
For the equation of the...
Let's do our quiz here. If you want to hang out real quick, I'll do that last bond enthalpy question because that will wrap up our Chapter 5 review. Vanadium is the key word for today. All right, I'm going to backtrack to that problem, but again, if you need to get to the